Alright guys, welcome to Lesson 5. To jumpstart your minds for Lesson 5, I have a little warm-up activity I want you guys to work on. So go ahead and pause the video here and see how much of this you guys can actually get done, okay? And when you unpause the video, we'll start going over it together. Okay, so first of all, what we have here in Part 1 is I've given you two functions. And I'm asking in Part A this weird looking symbol. What this means is it's we're taking the g function, which is g of x, and we're actually plugging it into the f function. And what that's called is a composite function. So once again, this is review, but it's been a while since you guys have seen this, so don't feel bad if you didn't get this stuff right. And that's why I'm giving you the warm-up, because I figure there are probably many of you who are having a hard time with it. So, like I said, for Part A, we're plugging the g function into the f function. So what that means is I'm going to take my f function, which is 4x minus 3. And what I'm going to do is I'm going to plug into the x the g function. Okay? So, I'm going to plug g of x in here. Now we could put g of x over here also, but let's put what g of x actually equals in this side. G of x actually equals this, right? So I'm going to put x squared plus 5 in there. And you could stop there. That's technically right at that point, but we can also simplify it a little bit, so why not? That's going to be 4x squared. 4 times 5 is 20. Take away 3 is 17. So that would be your final, most simplified answer there. And like I said, this is what we call a composite function. All right. Now, what about if we found f of g of 2? How would you do that? Well, basically that means you're going to take your composite function, right? And you're going to replace the x with 2. So I'm going to take this x out and I'm going to put a 2 in there. I wanted that to be a different color though. Same thing over here. We're going to replace this little x with a 2. And so that means it's going to be 2 squared, which is 4. 4 times 4 is 16, and 16 plus 17 is 33 would be the final answer for that one. Now there's another way that you could have gotten Part B even if you didn't get Part A. The way you would do that is you would take 2 and plug it into the g function first. So let's do that. That's 4 plus 5, which is 9, right? So g of 2 is 9. So now we need to plug 9 into the f function. Which is 36, take away 3, which is 33. Same answer, different way of doing it. Okay? But anyway, that's what a composite function is. Over here, we're doing something quite similar. But instead of working with actual equations, we're working with graphs. So let's go ahead and take a look at Part A here. They want us to find what is v of u of negative 1. Well, you start by working on the inside here. So let's do that first. Let's find out what u of negative 1 is. So we want to know what u of negative 1 is. So I know I need to look at the u graph right now. This is an x value. So I want to find where x equals negative 1, and I'm going to look up here, and the y value that goes with that is the answer. So u of negative 1 is that y value. So that's 1. Now I need to find out what's v of 1. So u of negative 1, which is being plugged into v, is 1. So that means we have v of 1. Now v of 1 means I'm going to look at the v graph. I'm going to find where the x value, now that's confusing because I just told you that was a y value. But over here on the v graph, it's acting like an x value. So on the v graph, I want to find where x equals 1. And look for the y value that goes with that. And the y value that goes with that is 2. Okay? So basically, find the inside value first, and replace that into the problem, and then work out the rest of it. So if you guys didn't get that one yet, I would encourage you to pause the video before you look at me going over part B, just so you get a chance to practice that again really quick. But here we go. V of 5, so I need to find out what is the V value. What's the V when x equals 5? So here's where x equals 5, that's right here. The V function's y value at that point is -2. So I'm going to replace V of 5 with -2. Now I need to look at the U function and find where x equals -2. That's like right here. And I need the y value that goes with that, which is 0, is the final answer. Okay? These are what we call composite functions. The reason that I'm giving this to you is because today we're learning how to find the derivative of a composite function. Right? Now let me help you guys understand this a little bit more from a slightly different perspective. As you guys know, when you find the derivative of a function, what that tells you is it tells you how fast that function is changing. So as x changes, how fast does the function change? Or another way to say that is, how fast is f changing with respect to x? Okay? But when you're talking about a composite function, an interesting thing happens. You have two functions that are working together to accomplish a task. So if you want to know how fast is this function changing with respect to x, what that means is how fast x is changing is going to affect how fast g is changing. And how fast g is changing will affect how fast f is changing. So let me go ahead and try to bring this to life for you a little bit with an example. Let's suppose you have a job, right? And in your job, the amount of time that you work affects how much money you make. So money is a function of time, right? And if you were to take the derivative of this with respect to t, that basically means that how much time goes by, how fast time is changing will affect how fast you're making money. So that will mean that you're making like $10 an hour. So the derivative of m with respect to t would basically be your hourly rate, or maybe your weekly rate of how much money you make, right? So that would be like dm over dt. So this is the change in the amount of money over the change in time. So dollars per hour or something like that, right? So time affects money. But as you guys know, we know now that time worked affects how much money you make. But you guys also know that the amount of money you make affects how much money you spend, right? So the amount of money you spend is a function of, I shouldn't use brackets there, that's not good. Let me back up. Let me use parentheses. The amount of money that you spend is a function of the amount of money you have. And the amount of money you have is a function of how much time you work. So, if you want to find the derivative of this with respect to time, what that means is, how fast does the rate at which you're making money affect the rate at which you're spending money? So that is what a composite function is. It's where you have one function plugged into another function. And our job is going to be to find out what's the rate of change, what's the slope, what's the derivative, what's the instantaneous rate of change of a composite function today. So that's what we're looking at. Let's go ahead and jump right into it. So today we're going to learn how to use the chain rule to find the derivative of a function. All right, so here it is. If you want to find the derivative of a composite function, you're going to use what's known as the chain rule. Okay, they call it a chain rule because just like the links in a chain affect each other, like since they're connected, one link affects the other link. Well, with a composite function, the inside function affects the outside function, so it creates a chain of events, so to speak. So they call this the chain rule. So the derivative of a composite function can be found by doing the chain rule. So what is the chain rule? Well, here it is. You do the derivative. You have an inside function, which is g, and you have an outside function, which is f. So what you do is you do the rate of change of the outside function, which is g of x. I'm sorry, f of x. So you take the rate of change of f, so f prime. Notice the inside doesn't change. And you multiply that by the derivative of the inside function. Okay? So in other words, how fast is f changing with respect to g is going to be multiplied by how fast g is changing, and the total will tell you how fast the entire composite function is changing. So if you multiply the rate of change of g with respect to x by the rate of change of f with respect to g, then you'll know the rate of change of the composite function with respect to x. So what we have here is we have, now I wrote it like this on purpose because there's another way you can write this. I don't use this a lot, but it comes in handy for people that do use it. I just don't use it a lot personally. But check this out. If I want to take the derivative of this composite function, it's f prime of g times g prime of x. So that means df over dg. G's on the inside, so it goes on the bottom. F's on the outside, so it goes on the top. And for this one, it's dg, because g's on the outside, and then x is on the inside. So you have df dg times dg dx. If you multiply these fractions together, the dg's cancel, and you're left with that. So what this means is that the rate of change of f with respect to x is the same thing as the rate of change of f with respect to g times the rate of change of g with respect to x. And that's what the chain rule is saying. How fast is f changing with respect to g times how fast g is changing with respect to x. Wow, that's a mouthful. I don't know. I hope I'm not confusing you guys. I'm just trying to say it in a bunch of different ways so you guys kind of get the idea of it. So that is what we call the chain rule. Okay? So you take the derivative of the outside, don't change the inside, times the derivative of the inside function. Let's go ahead and get down to business here. So part of the trick of the chain rule is the same thing as the others. You have to know when you're looking at these types of functions. So for instance, if I gave you guys this, what rule do you use? You would use the product rule. Or what if I gave you this? You would use the quotient rule, right? Or what if I gave you this? You would use the constant multiple rule. So you guys kind of need to be able to look at a function and realize, oh, okay, I've got a product, so that's a product rule. Oh, okay, I've got a quotient, so that's a quotient rule. Oh, I've got a constant being multiplied by a function. That's a constant multiple rule. So in the same way, you need to be able to look at this and go, oh, okay, that's a chain rule. Now, how do you know you're looking at a chain rule problem? You can tell it's a chain rule function because you will see an inside function and an outside function. You will see an inside function and an outside function. So how are we seeing that on this problem? Let's take a look. Don't you guys agree that 4x minus 3 is inside of a set of parentheses? there's your inside function. But what's the outside function? The outside function is taking that and raising it to the fourth power. So in green, we have the inside function, and in red, we have the outside function. Okay? Now, as you guys know, when you're trying to find the derivative of a composite function, which is what this is, what we do is we do the derivative of the outside first, and we multiply that by the derivative of the inside. Okay? So let's do that. Derivative of the outside times derivative of the inside. Well, let's start with the derivative of the inside. That's easier. So what is the derivative of 4x minus 3? It's just 4, right? The derivative of 4x is 4. The derivative of 3 is 0. So the derivative of the inside is 4. But what's the derivative of the outside? Well, how do you do that exactly? Well, the outside function is just something, right, to the fourth power. Well, how do we do that? You take the number in the front, you put it in the front, and you take 1 away from the power. It's a power rule. So to find the derivative of the outside, we're going to do the power rule. I'm going to take the 4 and I'm going to put it in the front, and then I'm going to take 1 off the power. Now, a common mistake people make here is with the inside. For this step, when you take the derivative of the outside, you do not change the inside. The inside stays the same. Okay? It's over here where you take the derivative of the inside. But for this first part, you do not take the derivative of the inside. So there it is. Now, we can simplify this a little bit. We have 4 times this times 4. I can put those two 4's on the outside of the parentheses together to simplify it, and it will look like this. Okay? Now, that's the chain rule. So you can tell you're looking at a chain rule when there's an inside function and an outside function. How do you do the chain rule? You multiply the derivative of the outside by the derivative of the inside. All right, let's go ahead and let you guys try one of those. See if you guys can find the derivative of this function. Pause the video, and when you unpause it, you will see the solution. Okay, so my inside function is 3x squared minus 2x. The outside function is in red there, and that's something to the 6th power. So to find the derivative of the inside, the green part, just apply the power rule to both of those pieces, and you get 6x minus 2. The derivative of the outside, you're going to move the power to the front. You're going to take 1 off the power, and that gives you 5. And we do not change the inside for that particular step. Now for this one, we're not going to simplify it anymore. If there was just a number over here, we would multiply it by the 6th. But in this case, it's a binomial, so we're just going to leave it like that. Okay. All right. We're going to do some more examples now to show you how the chain rule can be applied. So here we go. For both of these, what we're going to do first is we're going to rewrite them a little bit. So let's start with, I think G will be part C. Part C will be easier than B. Let's talk about part G first, or part C. First of all, what I'm going to recommend is rewriting it. So instead of having a radical there, I'm going to rewrite this as 3s cubed plus 4 in parentheses to the first power. So now I see my root is 3 and my power is 1. I'm going to rewrite it to be 3s cubed plus 4 to the power of 1/3. That's what I would recommend. Now that we've got it rewritten, we see that this is our inside function. And our outside function is a 3rd power. Okay? At this point, we're going to go ahead and find the derivative then. So, now just so you guys know, I'm not going to put equals here and then do the derivative, because the derivative is not equal to the original function. You don't want to do that. what I can do is I can put an equals right here because this and this are literally the same thing. They're just written differently. What I'm going to do now, though, is I'm going to draw a line here, and I'm going to say that g prime is equal to, and then I'm going to put the derivative. Believe it or not, if you put an equals here on your free response questions for your test, you said the original function was equal to the derivative, you would actually lose credit for that point. They're picky about those kinds of things. So let's go ahead and find the derivative. So the derivative of the inside multiplied by the derivative of the outside. So the derivative of the inside is going to be 9s squared. The derivative of the outside is going to be 1/3 to the power of negative 2/3. Move the power to the front, subtract 1 from the power. And we don't change the inside. In this case, we actually can multiply the 1/3 times the 9s squared. If you do 1/3 times 9, you get 3. So the best way to write your answer for this problem would be in the following fashion. 1/3 times 9 leaves me with 3. I'm going to put the s squared in the front, and then we're going to have 3s cubed plus 4 in parentheses to the negative 2/3 power. And I'm not going to do the thing where I put it in the denominator this time. You could, but it's just not necessary. Well, I guess I'll do it just in case. Because like I said, I don't know what it's going to look like on your test. They might do that or they might not. So the negative is going to move that part in parentheses into the denominator. Right? And once you do that, it becomes positive. Then another thing that they could end up doing is the 2/3 can be rewritten as a radical instead of a power. So you can write it like this. Okay? And that's where I'll stop. But I think this is fine. I think that's where they'll probably stop on your test, but it's possible that this could happen. All right, so before we do the next one, I want to let you guys practice part C. So why don't you guys do part G there. Go ahead and this guy in the middle. Go ahead and see if you guys can work that one out. I'll pause the video, and when you unpause, you'll see the solution. Okay, so as you guys can see, first of all, I rewrote it so that instead of a 4th root, it's a 1/4 power. Then I applied the chain rule. The derivative of the inside is 12w cubed. The derivative of the outside is the 1/4 with the parentheses raised to the negative 3/4 power, and the inside has remained unchanged. And then I multiplied the 1/4 by the 12w to the 3rd, and then I put that result in the front. So 1/4 times 12w to the 3rd leaves me with 3w to the 3rd, and we put it in the front. And this is actually an acceptable answer to stop at, but it might be good if you know that you can move that to the denominator and rewrite it as a radical as well, since it's a negative fraction power. All right, so there's that one. Let's go ahead and take a look at another one. Now, part B. I'm going to show you guys the easy way to do this first. Now, here's the problem. The easy way is not the obvious way. The obvious way would be for you guys to probably try to do the quotient rule, right? Doesn't that look like a quotient to you? So you really might be tempted to do low d high minus high d low, draw a line and square below. I'm going to say that's probably not your best option here, just because I think it'd be a little bit harder, honestly. But it works. It would work. You would be fine. You just have to do it correctly, okay? So what I'm going to do is I'm going to show you the way I would do it first. I'm going to do it a little bit of a simpler way than that. But afterwards, I'll let you guys practice the simple way, and then I'll show you how the the quotient rule can actually work, okay? All right, here we go. So the first thing I'm going to do is I'm going to rewrite it. And notice I put the equal sign, right? Because I'm not changing it. I'm just rewriting it in an equivalent form. So here's how I'm going to write it. I'm going to take this whole denominator here, and I'm going to move it up to the top. And I am allowed to do that so long as I make that power a negative. it's working backwards from what we usually do, right? Usually it's negative and we move it to the bottom to make it positive. But in this case, we're working backwards. I'm taking the positive denominator and moving it up to the top and changing the power to a negative. Why would I do that? Because it makes the chain rule a lot easier to apply. Okay, so we have 2s squared minus 1 is the inside function. And then we have 3 parentheses to the power of negative 4. So, first things first, derivative of the inside. The derivative of the inside is 4s, so I'm going to put that there. Now let's do the derivative of the outside. So the derivative of the outside, I'm going to take that red negative 4 and multiply it times the 3, that's negative 12. And then I'm going to take 1 away from the negative 4 to make it negative 5. And we don't change the inside. All right. And then, yes, I'm going to go ahead and I'm going to multiply the negative 12 with the 4s. And that's going to give me negative 48s, parentheses, 2s squared minus 1 to the negative 5th power. So you can leave your answer like that, or you can move it back down into the denominator so it looks like this. Either one of those are acceptable answers. I don't like how this 5 looks like an S so much, so I'm going to rewrite it. And even that's not a very good 5. Oh well. One more time. Ah! Haha. Good 5. All right, so there we go. This is an acceptable answer, but it's possible they'll write it like that, just so you know. Okay? So I'm going to have you guys try one like that, and then I'm going to show you how the quotient rule can actually work, even though it's a little bit harder. So I want you guys to do this one over here. Go ahead and pause the video, give it a shot, and then when you unpause it, you will see the solution. Okay, so step 1, I rewrote it. Moved the denominator to the top with a negative exponent. Step 2, did the chain rule. The derivative of the inside was 2. The derivative of the outside is negative 6 times 2x plus 3 to the negative 4th power. Then I multiplied the negative 6 and the 2 to get negative 12. This is an acceptable answer, but you can also write your answer like this by moving the parentheses set to the denominator with a positive power, and that's that. Now, I want to, you don't have to watch this if you want to, because quite honestly, if you ever see a problem like this, I wouldn't even approach it this way. But I want to show you, because knowing how to think through a variety of circumstances is helpful. So what I'm going to do now is I'm going to go ahead and I'm going to solve your problem here, but I'm going to do it using the quotient rule instead. So let's say you saw this and you forgot what Mr. Bailey had told you about rewriting it. Okay, and you went ahead and you just started doing the quotient rule. Okay, so it would be low. Oops, that is not what I wanted. Let me fix my pen a little bit. So since it is a quotient, the derivative can be written as low d high, which is 0, the derivative of the top, which is just 2, is 0, minus high, which is 2, d low, and that's where things are going to get interesting. I'll leave that like that. Draw a line and square below. Now, this was low d high minus high d low, so the derivative of the bottom is where it gets interesting. So if you want to take the derivative of this, you still have to do the chain rule. Okay, you still have the derivative of the outside times the derivative of the inside. So the derivative of the inside here is 2. The derivative of the outside is going to be 3 times the quantity squared, and then 2x plus 3. Now in this case, this 0 cancels out this whole thing. 0 times anything is 0. So that's just gone. And then we can multiply negative 2 times 3, which is negative 6, times 2 is negative 12. So we get negative 12, parentheses, 2x plus 3 squared over 2x plus 3. 3 times 2, that's the power rule that I use, not the derivative power rule, but the old pre-calculus exponent power of a power rule. 3 times 2 gives you 6. And since you have the same thing on the top and bottom, you subtract the exponents. So you could have done it this way. And it's good to know a variety of ways to do things, to stay fresh. And that way you're able to think on your feet and handle a variety of circumstances. So it works. Now, the only time, though, that you would want to do the way that I showed you at first on this, and so, well, actually, let me back up a little bit. This is a much more powerful method than what I just showed you, in my opinion, just because it'll always work. For this guy over here, the way I showed you where you rewrite it first like this, that's only going to be, in my opinion, easier if the top is just a number. But if I had something else up here like x squared minus 5, at that point I'd say forget it. Just go ahead and do the quotient rule. Okay. So when you have just a number on the top, you can rewrite it like this and go for it. But other than that, it doesn't really make much of a difference. However, I'm going to try to explain something. I hope I don't confuse you guys even more. However, let's say I did have this. Let's say I had that, right? Let me erase this stuff here real quick. So let's say I had this quotient rule here, right? You could do the quotient rule on that and get the right answer. But you know what else you could do? You could actually do the rewriting rule. You could take the bottom. You could move that whole thing up to the top. Just make the power a negative, right? And now it's not a quotient anymore. Quotient rule. What is it now? Now it's a product rule. The unfortunate thing is it's a product rule with a quotient inside of it. But I'm just showing you guys things to make you think. We're actually going to talk about problems that will do that kind of stuff a little bit more next class. Just kind of giving you a sneak preview. For today, just stick with the way I showed you initially, but there you have it. All right, let's take a look at another type of chain rule problem, but this time it's going to be having to do with tables. Okay. I'm going to start with part 2. I just feel like part 2 is a little bit more understandable based on what we've learned so far. So we have this function. We're going to say that h is a composite function. H is a composite function because it's one function being plugged into another. It's f of g of x. Now, when you want to find the derivative of a composite function, what we do is we do derivative of the outside times the derivative of the inside. So it's going to be f prime of g of x times the derivative of the inside, which is g of x. Now that we have the derivative, we're ready to find the slope at the specific point where x equals 1. So we're going to go ahead and plug in 1 now. Oops. All right, so let's get down to business here. So first of all, let's do g prime of 1. That's pretty easy. G prime of 1 would be right here, negative 2. So I'm going to replace g prime of 1 with negative 2. Now for this next one, we did this on our warm-up today, right? You need to do the inside first. So what's g of 1? What is g of 1? G of 1 is 3. After you do the inside, then you can do the outside. What's f prime of 3? It's negative 1. So, well, I shouldn't circle that because we're not done yet. Negative 1 times negative 2 is positive 2. So there's your final answer. So step 1, do the chain rule. Step 2, plug it in. Step 3, do your chart. But when you do your chart for the composite piece, find the inside first and then do the outside. Okay? So Let's do another one, and then I'm going to let you guys practice this a little bit. Let's go ahead and do part 1 now. So h of x apparently is equal to h of x is the function f of x being squared. So in this case, we have a inside function, which is f of x. That's my inside function. And then my outside function is the quantity squared. Okay, so if I wanted to find h prime of 1, then I'm going to find, that means I'm looking for the derivative of h, which means we have to do the chain rule. So derivative of the inside multiplied by the derivative of the outside. So here we go. We have the derivative of the inside, which is going to be f prime of x. The derivative of f of x is just f prime of x. And then the derivative of the outside, we're going to do the power rule. So moving the 2 to the front, parentheses, subtract 1 off the power, it's 1. And we end up with, not changing the inside, right? We end up with that. Okay, now we're going to go ahead and do h prime of 1. We're going to plug in 1. We don't need the power of 1 there. I'll just leave it off. All right, here we go. So let's do f prime of 1. On our table, f prime of 1 is -1. And then for this piece, we're going to do the f of 1 first. So f of 1 is going to be 4. Bring down your 2. And then 2 times 4 is 8. Times a -1 is -8. That didn't come out well. I'll write it over here. -8. Okay. So that's the chain rule using tables. Okay, so I'm going to let you guys try one of those here. Go ahead and give these 2 problems a shot and pause the video, and when you unpause it, you will see the solutions. Okay, and there's your 2 solutions. I'll let you guys go ahead and pause the video there and study them if you need to, but for number 1, I got -54, and for number 2, I got -9/4. All right. And that's where we'll go ahead and stop for the day. There was a little story problem at the end, but I think we kind of addressed that kind of stuff at the beginning, so we're good. I'm going to stop there, and you guys are good to start your 1.5 homework, and we'll see you guys next time.